Hello students and welcome to today's lesson, which is essentially on types of questions that we could get for our haloalkanes here. Okay, and so our goal here is just to be able to take any of these questions that we get and to think like a chemist. How can we solve this question and what factors do we want to go ahead and analyze here? So we have our first question here, which says to show the mechanism, including appropriate curly arrows for the hydrolysis of 1-chloropropane by alkali. Okay. So what we're going to go ahead and do is we're first going to draw out our 1-chloropropane. Okay. So propane, we have 3 carbons, and we have a Cl here, and we have our hydrogens coming off here. Okay, and it says that it's 1-chloropropane, so that means that we know that this is a primary haloalkane. Okay, so right away we should be thinking, okay, any reaction that we're going to do is quite possibly going to be the SN2 reaction. Okay, so the SN2 reaction, then we also know that we have some alkali. Okay, and anytime that it says hydrolysis with an alkali, we're immediately going to go ahead and think that we're going to have the OH minus. Okay, even though hydrolysis typically has us using H2O, the reason that we'll use the OH minus is that we have both the OH minus and H2O in that solution, but this one is obviously going to form a better nucleophile because it has a full positive charge. Okay, so we know that we're going to have this attack here, and we're going to have our curly arrow. Okay, and then once we have that attack with the curly arrow, we know that we're going to get our temporary bond. The chlorine is going to be temporary bonded as well. And then we're going to have our last step, which is our and then we'll have our full chlorine coming off right here. Okay, and that's really all that we need to do to show this one, in particular showing that the OH is coming in, and to highlight this curly arrow right here. Okay, and that's our first problem, just showing what happens when we have an SN2 reaction. Okay, and we can tell that it's an SN2 reaction because it's a primary halogen. Okay, let's go ahead and work on the next one. And the next one first has us drawing the displayed formula of 2-chloro-2-methylbutane. Okay, so right away we see that the chloro is on the second carbon, and it looks like we also have a methyl group on that second carbon. So we'll go ahead and draw it out, and then it says to show the mechanism for the hydrolysis of the 2-chloro-2-methylbutane by alkali. Okay, so let's go ahead and get rid of all of this right here. Okay, and it says that we have 2-chloro-2-methylbutane. So butane, 4 carbons, 2-chloro, 2-methyl. Okay, and so the first thing that we should notice before we do anything else is that once we have drawn this, we should notice, hey, wait a minute. This right here, this is a tertiary carbon. It has 1, 2, 3 carbons around it. Okay, tertiary carbons, we can't use the SN2 reaction. Therefore, we're going to have to use an SN1 reaction. All right. So the next one is it says to show the mechanisms for the hydrolysis of 2-chloro-2-methylbutane. by an alkali, okay? So this particular reaction is the SN1. And the SN1, remember that we have our first step and the first step, our rate limiting step, is just that we have the electrons moving on their own from the carbon bond to the chlorine. The second step is where we have the complete carbocation. The third step will end up being when we have the OH that's attached to it here. Okay. And then in this case, because the chlorine's not attacking, doesn't have to attack the OH, the chlorine, we can just go ahead and leave it here at this step because we don't have the chlorine attacking and helping it because it's with the alkali right here. Okay. And this is all that we have to do to show this one. Okay. Now these two questions, question 1 and question 2, their whole point in this question is to evaluate, first, can you tell when a reaction is going to be SN1 versus SN2? And the second thing they're trying to evaluate is, can you explain and understand what's going on with an SN1 versus an SN2 reaction? Can you explain both of those reactions there? Okay. Next set of questions here. It's asking, why does the hydrolysis of a halogenalkane happen more quickly with OH ions than with water molecules? Okay. And this again is something that we can explain, simply by, drawing it out. That here, in OH molecule, we have a full charge here. Okay. Okay, we have a full negative charge that's associated with this molecule. Whereas with that water molecule, we do not have a full charge. Okay, so even though both of these are nucleophiles in that they want to go ahead and bond with something else and that they have this electron density on the outside, the one that has the full charge is definitely going to be a stronger nucleophile because it has a negative charge, so it's going to want to bond with something positive as soon as possible. Next, it asks us why we would use silver nitrate to investigate the rate of hydrolysis for the halogenalkanes. Okay, so we have to go ahead and explain why, when we take one of these molecules right here, why we would have silver nitrate with it. Okay? And the answer has to do with what our waste product was. So our waste product was this chlorine molecule. Okay? Silver nitrate is AgNO3. And AgNO3 has silver in it. And remember, silver is one of those compounds that doesn't really want to dissolve in solution. So that means that the silver is going to go ahead and bond up with the chlorine. Okay? And in fact, what we have is we have the silver, which has our positive charge to it. And it's going to go ahead and be aqueous. We have the nitrate, which has a negative charge to it, which is aqueous. And then we have also added to this the silver ion. And the silver ion, normally that is aqueous as well. So we have all three of these ions. When the silver one and the chlorine come together, though, they're going to make silver chloride. And silver chloride is not aqueous, and it makes a solid. And then we'll have our nitrates, and all nitrates are soluble. And that one's going to be just hanging around there. So we use this to determine the rate, because as the rate goes forward, what we should notice is that we should get more solid being precipitated out here, because we just keep producing more and more silver chloride. Okay? And here it wants the ionic equation for what happens when it precipitates, and this is exactly what happens when it does precipitate here. So we already have our ionic equation. Okay. And in fact, this one right here, we wouldn't end up needing that one at the end. So if it asks for our simplified ionic equation, we would be left with just the Ag plus Cl minus, and we get AgCl. We've had to mark that that's solid and that both of these are aqueous. Remember, whenever it does ask for an ionic equation, you will need to use your states of all of those molecules. Okay. The next set of questions is asking more about ammonia. Okay. In question A, it's asking why ammonia and amine molecules can act as nucleophiles. Okay. So we're going to go ahead and, in order to understand this, we're going to have to draw it out. And ammonia is NH3. And what we notice with the ammonia is that it has these 2 electrons here. Okay? So we would just go ahead and automatically state, hey, the unpaired electrons in ammonia are the reason that it acts as a nucleophile. Okay, so that's for question 1. Now question 2 states that when ammonia is reacted with an excess of halogenalkane, a mixture of amines can be formed. If we start out with an excess of 1-bromopropane, give the structural formula and name of the tertiary amine formed. Okay, so here it's asking for a tertiary amine. Okay. So let's go ahead and think about this one right here. We haven't talked too much about like the actual amine groups going on, but we can go ahead and take a look here and say, all right, we have a propane molecule, and on it we have bromine. Okay. This particular molecule looks as if we are going to add ammonia to it, okay? So we know that right here, we're going to add ammonia to this particular molecule. So let's go ahead and take a look what would happen to our molecule when we added this ammonia here. This is going to go through a SN2 reaction because this is a primary halogenalkane. So that means that we're going to have this right here come in and attack this bond, and we're going to end up getting 2 products that come out of it. Okay, and then we're going to end up knocking off one of these hydrogens, and so we'll have HBr. Now, what I want you guys to take note of, okay, remember, this nitrogen had a set of unpaired electrons, okay? All right, so we have a set of unpaired electrons here. Notice what this is asking here. It's giving us some information. It's saying that it's when it's mixed, a mixture of amines can be formed, okay? So this is saying that both ammonia and amines can act as nucleophiles. The question is giving us some information to go forward. And when it asked our first question, it said, hey, look, it's these electrons here on the ammonia that are acting as a nucleophile. Now look, we still have those electrons right here, which means that now this molecule can act as a nucleophile. Okay? So that means that this molecule can then go ahead and instead of just sitting there all willy-nilly, it also can attack our excess of 1-bromopropane. Okay? So this one can now act as a nucleophile. Okay? And this one's also going to go ahead and give a waste product of HBr. Okay? Because we're going to knock one H off of our hydrogens here when we make this bond here. Or really the bromine's going to attack one of those hydrogens. Okay? So now we have a secondary amine. But now look, we have another issue. Okay? This product right here, as a secondary amine, still has those 2 electrons on it. Okay? So it can still act as a nucleophile. Okay? Which means that we can end up having a tertiary one as well. Okay? And this is going to have the waste products of HBr. Okay? Alright, so this one right here would end up being one of our end products. Okay? Now, for all of these, we're going to end up having some combination of all of these in our end products. So all of these are possible products that we could end up having. Luckily, it asks us to just go ahead and name this last one right here. And we could go ahead and say that it's dipropyl, because we're going to have 2 propene groups. Okay? Or we have 2 propyl groups, and then it's propanamine. Okay? So we have these 2 right here. Alright, and so that's how we can go ahead and answer that question. And notice that this one right here, what it is looking for is it's saying, hey, we're taking our information about what we know about nucleophiles and let's apply it to something else. Okay, so we have our nucleophiles and we know that anything that has this lone pair of electrons is going to want to bond up and, form a substitution reaction. Okay, that's what it's giving us the initial information for. And once it gives us that information, it wants us to apply it with just a little bit of information. And that's what this is saying right here. It's saying that, hey, we know that if we have an excess of this, that it forms this. Now go ahead and theorize the process by which this happens or how this happens, and take the information, take your base knowledge and use it. And that's what this type of question is trying to get you to do. Okay. Number 19 is going to be our first question that comes from the practice test. And it's saying that alkenes are saturated hydrocarbons. Okay. Which type of reactions are alkanes likely to go? Okay. So we know that it's saturated. Okay? It is saturated. We cannot add any more to it. Okay? So therefore, any type of addition is going to already be something that's not possible for us. All right, so we have all of our additions. We automatically know that, hey, they're saturated. We cannot add any more to it. So that leaves us just our substitution questions. Okay. When we have a substitution question, we're then going to have to look to see, hey, is it going to be a nucleophile? Is it going to be an electrophile? Or is it going to be a free radical? Okay. And from what we described earlier, and especially since these are saturated hydrocarbons, we know that it's going to be a free radical that's going to go ahead and bump everything off there. Okay. And remember this from the free radical propagation that we went ahead and indicated from before. Okay. Now, this question could have a possible trap to it. So remember that we can also have nucleophilic addition or substitution. But notice that that type of substitution, that type of reaction, isn't possible here. Okay. So the two options that we could have had to add to an alkane, a saturated alkane, is that we can either have the free radical, and that's where we have the chlorine coming in like this, or we can end up having the nucleophilic addition or the nucleophilic substitution. Okay, those are the two ways that we can go ahead and add on. Since we don't have the nucleophilic substitution option, that means that we're left only with the free radical, which is why C is going to be the answer for this question here. Next is 23. Okay, 23 was another question that was from our practice test. And what I want you guys to note is that it says that we have this tertiary bromoalkane. Okay, so it already tells us that it's tertiary, so we automatically know that this has to be an SN1 reaction. And it reacts with aqueous NaOH. Okay, so we know that we're going to have a nucleophilic addition, a nucleophilic substitution, and it's going to be with the OH, and it's showing the reaction pathway. Okay, which point in the diagram is correctly identified? Okay, and so it's asking us to identify X and Y. Okay, so X and Y, we have to remember that X is when we're going to have the curly Q over from, that's our first step, where we have our curly Q over. Y is going to be where we have our carbocation. Okay, so we have to go ahead and think, okay, what's supposed to be in each step here? Okay, it says X has the carbocation, and we're going to think, nah, that's Y's spot. X, it's showing right here this bonding between both of them at the same time. And what we should notice is that, hey, that's not actually how this type of reaction goes here. Okay, this is showing an SN1 reaction. And the same is going for this bottom one right here. It's showing an SN2 reaction where the two molecules are interacting with each other. So we're like, no, it can't be B or C. Therefore, the answer has to be C, where Y is the carbocation right here. Next was the 24, and 24 is having us work with bromoethane and chloroethane. they're added separately to water, a hydrolysis reactions occur, which compound hydrolyzes more rapidly, and what is the mechanism. Okay. So we know that this is adding to water, which means that automatically we're thinking that this is going to be nucleophilic substitution. So we see, hey, nucleophilic substitution, nucleophilic substitution. Then it's asking which one's going to react quicker. Okay. And we have to go ahead and remember, all right, which kind of halogen alkane is the more reactive, and it's always going to be the larger one. Therefore, 24 will be B because it has both bromoethane and the nucleophilic substitution. Okay. Hopefully this should help you guys understand all of the questions for this particular section. And if you have any more questions on the actual problems, please let me know. Okay. And as always, stay lazy.